Well, hi everyone. On behalf of Ideas, I'm very excited to have you all today. Today we have a raining evening, but I'm really thankful and I appreciate everyone who can join us today. So before we jump into the webinar for today, today's topic is feature engineering for hyperdimensional decision surfaces. So let me just briefly remind you what is Ideas, and for those who are still joining, so they can have some time to join. So, again, big thanks to everyone who can join us today, and for those who are watching the video on our YouTube channel, hope you can join us online next time. So Ideas is International Data Engineering and Science Association, and it's a non-profit organization based in Los Angeles. Our mission is to bridge the gap between academia and industry. So basically, we are very excited about data science, machine learning, and AI, and also blockchain. And we are sharing that enthusiasm with others. And we're here to connect these passionate people from data science background with each other to share the ideas and thoughts and just simply collaborate. So this is the roadmap. We started 2016 and we are moving on, and we are hosting conferences across the country. 3 years ago, our first conference was held in USC campus. And later we started to grow rapidly, organizing conferences on different topics, such as different topics in different countries. The different areas of the country, like New York, Chicago, Boston, LA. Recently, we held SoCal conference in Los Angeles Convention Center. That was in November. This is the photo gallery. This is the very first one, SoCal conference at USC. This is the New York Blockchain Leadership Connect. This is Chicago Blockchain Leadership Connect 2018. This is SoCal Conference Pasadena. We usually hold SoCal conference each year. So this year we're also looking forward for upcoming SoCal conference. This is the last one in Los Angeles, the very big one. Apart from just conferences, we also held meetups at different universities like Harvard, New York University, MIT, Chicago, Illinois. We also do different meetups and hackathons. So yeah, if you don't know about us, you can still go to our website. Just simply write an email to us. We also have a Facebook page, LinkedIn profile, Twitter, and YouTube channel. This is the QR code for our YouTube channel. So if you missed our past webinars, you can simply go to our YouTube channel and watch it. So yeah, now let me introduce our wonderful speaker guest for today. His name is Max Izatt. He's a director and a chief data scientist in the Insight Analytics group at Hitachi Consulting. Max was trained as a theoretical chemical physicist at MIT and University of Chicago. He has a lot of experience working at laser projects division at Sandia National Labs. Later, he became a lead quantitative developer at Salomon Brothers. He worked at Tokyo, Japan, and New York. He also worked as a director of International Data Center at Arthur Andersen, and later he founded CentraLytics Corporation, which provided software for quantitative finance, algorithmic trading, biostatistics, and quantitative marketing. So CentraLytics intellectual property was later successfully acquired with Microsoft footprint. So yeah, this person is very aspiring. So welcome, Max. We're here, very excited to have you today, and thank you for doing this. Very excited for your talk.
Well, thank you, Dalia. I'll share now.
Sure, yeah.
Okay, I'm going to stop your screen. There it is. And let me, there we go. Let me just go. Well, it's so good to be with you. First of all, I'm very grateful to be with Ideas. I was at the Chicago conference. I saw your roadmap there a minute ago, and on AI and blockchain at the University of Chicago, and it was a wonderful day. It was a really great gathering of people. I am Chicago-based, so that was my home turf. Tonight, I don't think you can see behind me too well, but I'm in Midtown Atlanta near Georgia Tech, and I haven't been on this campus in years and years, but so I'm away from Chicago tonight, but so happy to be with you. So the topic is, I just thought I'd shed some light. I'm often asked, how is this stuff applied? I work for an industrial company now. Hitachi is a global conglomerate of almost 1,000 different engineering companies, from heavy chemical and machinery and rail and maritime applications and materials. And all of it touches my desk when we consult on it, which usually means installing it. So I'm these days a very applied scientist. This fancy title I have of data scientist, I just see myself as a working mathematician, really. I'm a data science lead and have had the opportunity and honor to be the chief here for a while. That role will eventually migrate to another person on our team, but it's really fun to do it. So I get to see a lot of this stuff, and I have to apply it, install it, and retrofit it, and can't leave until it works. So I thought I'd shed some light on kind of what I do for a living, because when I give these talks, I'm often asked, how do you bridge this from an academic background into a practice area? And with IoT emerging so strongly as a success area, then I think maybe I have a perspective here that you might enjoy. So tonight we have just a data set in 2-space, and I thought we'd just beat the heck out of it and kind of apply some machine learning and some data science. Now, when I use the term data science, I mean machine learning in the pursuit of a scientific answer. That is cause and effect instead of just correlations. And so I don't mean to say optimization theory that has given us our algorithms. I'm going to use data science to mean the prosecution of a scientific result of a causal factor using machine learning techniques. So we have a data set, and I thought I'd remind ourselves or inform us, as the case may be, on how this radial kernel technique works. It's so successful in, say, support vector machines, and then illustrate a nonlinear decision boundary here, and just with kind of a cartoon type heuristic, and map it to hyperspace. And then I have in the R language, a polynomial kernel, because it would be a little easier than an exponential, which is the radial kernel here. So we'll kind of work through what a kernel is and how it helps us, and then perform some machine learning, chase some second order features, and about that time we're going to catch our breath and actually do some physics and try to develop a hypothesis, and then prosecute a data science study, compare and contrast that with kind of a machine learning result. And then this is actually a timely topic. So just a week ago yesterday, in the news, you may have seen an article that I'll show you, and we'll kind of bring some of my ideas and map it to that news. So here's our data set tonight. It's a GBB, a good, better, best type of categorical data set. Maybe this came from a public health study or some kind of a survey. And what it is, it's a mapping of 6 categories: underweight, normal, pre-obese, and 3 categories of obesity mapped to height and weight. So it's a 2-space with just this crazy nonlinear kind of messy decision boundary. And we're going to try to say something, or one or more decision boundaries, and we're going to try to say something about the pre-obese as a predictor. We're going to try to predict on that is categorize it, and see if we can't discriminate on using height and weight or functions of height and weight as causal factors. So just as an offside here, let's remind ourselves of a Taylor series. I'm going to use this as a motivation for these kernel techniques and for feature engineering in general. I don't want to beg too much meaning, because a kernel and polynomial feature engineering are not the same thing. But let's just remind ourselves in your school days, if you go back to your calculus study, remember you can expand a function in a power series, and the prefactors there are the various derivatives with the factorials or functions of factorials underneath, depending on what function it is. Remember, these things have a radius of convergence. And so I can expand analytically around a point A in some power series of the difference of my position minus that point A in space, perhaps in space. And the functions the function f evaluated at that point A gives me the prefactors when scaled with a factorial. Now, that was the work of Taylor. Remember, Maclaurin did a lot of work around the origin itself. And remember this radius of convergence here, which is a function by function result. And also remember the error term, by the way, is the ratio of the nth plus first term in units of the nth term. Remember, the exponential function converges for all x. So we've got all powers of x converging for all x. So it's kind of a neat function. And so it's compelling to kind of look at that when we think about feature engineering, and just keep that in the back of our mind. That if I expand in all powers of x, then I have a convergence around X for all distances from X. Well, the radial basis function, which Baptic used in support vector machines, and we use it in other classifiers. Let's just look at that for a minute. Here it is. It's this norm. It's this norm in units of the variance. I mean, that sure looks like a Gaussian, doesn't it? Well, it is. Of course, we're missing the prefactor of the radical of 2 pi times the variance, but never mind that. And remember, we just saw that we can expand that in any power of X, and it kind of looks a little messier when you're in a vector space, but don't worry about that. So let's just keep that in the back of our mind, that if we map higher order features, that we're kind of doing something that's in the spirit of an analytic continuation around a point. That's what I wanted to say about that. So this example here, we're in a 2 space. I think we could all draw a decision boundary between the blue species and the red species, but here it gets a little messier, doesn't it? There's no, actually, when you have a triangle, here I have a picture of that. When you have a triangle of one species in the plane and the other species encroaches on it, it turns out you cannot draw in Euclidean space a decision boundary there. I'm not prepared to prove that tonight, but maybe you saw that in your high school phase or something. But it turns out that if I can use this kernel trick, and that's not a pejorative, it's called the kernel trick. If I can employ this kernel trick, then I can lift that into a higher dimensional space. Now, if I looked at it from this point of view, I'd just get back to here, wouldn't I? It's the same thing. But if I can take this point of view from this region looking in this direction, then I have this hyperplane in an n-1 dimensional space. That is, in a 3-dimensional space, I can have a 2-dimensional hyperplane. And I can draw a perfect decision boundary between those 2 species. So that's the motivation for this so-called kernel trick. Well, here is a polynomial kernel. The exponential kernel, the radial kernel, is a bit more involved. But let's cover the idea of what a kernel is. This is a polynomial kernel. In 2 space, I have 2 vectors, u and v. U is the vector 1, 2 in 2 space. V is the vector 3, 4. And let me remind you of the Hadamard function. That is a function in a space that takes 2 vectors in that space and returns another vector in that space that is defined as the product of each vector element in the space. So if this were a 10 by 10 matrix, I mean to say, then the matrix element 1, 1 would be the matrix element 1, 1 of the P matrix and the matrix element 1, 1 of the Q matrix. It's different than a matrix product. This is not a transpose times the other vector. This is just a raw multiplication of the vector elements. That's what's called a Hadamard product. So we have this Hadamard product. It takes 2 vectors in 2 space and it returns the vector elements multiplied and gives back a 2 space vector. The self product is this function we're just kind of making up. It takes a vector in 2 space again, and it just gives the cross terms of the first and second vector element of that vector itself. And so if we sit down and define this kernel function, it's this crazy thing. It's the Hadamard of S and T, and we sum that up. The Hadamard of S with itself, and sum that up. Times the Hadamard of T with itself, and sum that up. And then add up the self products of S and T. We would have a function. Now, I think it's fair to ask, where the heck did that come from? And the answer is a lot of smart people thought about this for a long time, and they gave it to us. That's where that comes from. But if we were to calculate the kernel, this kernel function on these 2 vectors u and v, we would get this a number, which is 108. Let's refer to that as the kernel digest. Okay, so let's set that aside for a moment and now create another function called phi, which we're going to call the kernel certificate. Now it takes a function in 2 space, a vector in 2 space, and it gives you back a phi vector. It does that by regurgitating the 2 space vector and adding to it 3 more vector elements: the square of the first vector element, the square of the second vector element, and the cross term of the 2 vector elements. So I give it a 2 space vector, and I get back a 5 space vector. So let's do one. If I have u of 1, 2, I have the phi vector, that's the kernel certificate of this 2 vector, is the vector 1, 2. It regurgitates it back at me. I get the square of the first, which is 1, the square of the second, which is 4, and the cross term, which is 2. So I have the phi vector 1, 2, 1, 4, 2. Now let's calculate the kernel certificate of the v vector. It is the vector 3, 4. Well, it regurgitates that right back at me, 3, 4. The square of the first is 9. The square of the second vector element is 16, and the cross term is 12. I have the 5 space vector 3, 4, 9, 16, 12. Okay, well, so what? Well, here's our kernel. Remember, we calculated the kernel in 2 space. The kernel digest is 108. Well, if we look at these 2 kernel certificates, first on the vector u and the vector v, we have these 1, 2, 1, 4, 2, and 3, 4, 9, 16, 12. And it turns out if we take a vector product, now this is not the Hadamard, this is the good old-fashioned u transpose v. This is the vector product, the kernel certificate of u in 5 space, crossed with the, dotted with the kernel certificate of v, again in 5 space, we get back this digest 108. So this 108 kernel digest is very fundamental to this geometrical kernel trick, or the kernel transform. Now, it turns out that a kernel is only defined for something that has a certificate. And there's only so many of them. I mean, if you pick up a good quality machine learning text, you'll certainly find the radial kernel, which I like just because of the analytical properties of an expansion into a power series with convergence for all x. I like that. That's a personal thing. But there are 3 or 4 other ones, but there are only 3 or 4 other ones that are really out there. There are only so many of these that have been thought through. Well, so what we're doing is we have this crazy, a nonlinear decision boundary here. I mean, that's my mouse doing that, so sorry for the artwork. But what we aspire to do is to use this kernel trick to lift it into a higher dimensional space. Now remember the other graphic. This is not a 2 space. I'm depicting it as a 2 space. But remember when and the coupling is the kernel trick here. Now remember when Vatnik did this for support vector machine, he gave us it's really genius. He has some guarantees on the width of that gap so that I can just drive a decision boundary just right down the middle of that space. So this is a 5-dimensional space in the polynomial kernel that I just showed you. And remember, in the radial kernel of support vector machines, it is indeed an infinite dimensional space. So let's do some data science together. We've got our good, better, best data set. We've got our height and weight, or our fundamental measures in the lab. And so let's do, so this is the, here it is, it's height in inches and the weight in pounds. I've got my classifier here. And we do some tallies here. There are 1860 pre-obese, and we're gonna mark that up. And Dahlia, I'm seeing here, I'm gonna move that. I don't know if you see that, but the webcast is in my way. So here's our pre-obese. We're going to mark the pre-obese guy as 1, and everything else is 0. And here's our data frame. And let's just table the Y here to make sure I didn't screw it up in 2 lines of our code. It looks good. I've got 1860 true and 8140 false. Now, remember, my baseline now is 81.4%. That is to say, the baseline of any machine learning study is the default majority class, in this case false. In this case, my guess, if you held a gun to my head out of the blue and said, what's your guess? My guess would be that you're not pre-obese. You have an 81.4% chance of not being pre-obese. So we have to do better than that if we're going to add any value at all. So here's our multivariate regression, logistic regression. Now let me remind you, I think I'm telling you something you already know, but remember, we have to embed these log odds go into a signal, and I chose a logistic function here. So I have to calculate these prefactors times my x vector for each experiment I have, in this case 10,000 of them. And this gives me the probability that it is true. Parameter for a problem parameterized by my beta vector, then I apply a threshold, some threshold, to classify true on the threshold or false against the threshold. So this is not a multivariate linear regression, this is a multivariate logistic regression, just to remind us of that. It turns out this doesn't work at all. It's horrible. So I have the threshold here along the bottom. And you can see the accuracy never does get above my 81.4%. And the true positives fall off dramatically. And I have this crazy threshold here of, I think that's like 22%. This is just entirely unsatisfying. So despite the fact that it appears these are statistically significant factors, in fact, they don't work as a classifier. Now, a word about this p-value here. That p-value doesn't pertain to me right now. Even though they're beautifully statistically significant, I'm not working with a hypothesis here. And I suppose we could p-hack it. There's a term for that, p-hacking, to look at the statistically significant features and to pursue them. So that does give me some notion of strong correlation, but there's absolutely no idea of causation. in this study whatsoever. So these p-values, I may as well ignore them, although it's satisfying to have them. But indeed, as a classifier, it doesn't work. And in fact, if you calculate the area under the curve, under the ROC curve for height and weight, you would find that neither one does better than the baseline. Well, so what do we do? Well, we engineer some features. Let's do some machine learning. So I'm going to chase some second order features. So let's take our baseline set that we measured in the laboratory. I'm going to take the square of each, the cross term, and the ratio of one to the other. These are my second order features, and let's do some more machine learning. So here they are. I'm marking up my pre-obese with a 1 and 0. I've got my 2, 4, 6, 7 features here. So in seven dimensions, I'm going to try to draw a 6-dimensional hyperspace. They're all relatively statistically significant. It's too bad that doesn't pertain to me. I don't have a hypothesis. But it turns out it kind of sort of works, doesn't it? My true positives are falling off. My threshold is a little more satisfying. There's nothing magical about a 0.5 threshold, but you know, it's starting to look more like something I might want to do. Very choppy. Now, Professor Edward Tufte would be very upset with me, wouldn't he? He says never depict data when you don't have the origin in your map, and indeed I don't. You can see that although this seems to be falling off drastically, I'm still at 3 9s here. So you know, so that's just poor graphics. But anyway, this is unsatisfying to be so choppy. So you know, at this point, and by the way, if you calculate the area under those curves, something interesting happens. The square of height and weight are no better than the linear terms. The cross term is worse, but the ratio seems to be some signal in that noise. That's kind of interesting to me. And at this point, you know, I mean, I am a physicist, I suppose, so I'm just compelled to kind of, let's do some physics. Can we develop a hypothesis about this thing? So I'm going to pivot from raw machine learning into some kind of the pursuit of a scientific cause, not just correlations. Well, I mean, we have height and weight. So aren't we kind of cylinders, we human beings? I mean, we're kind of cylinders. We're kind of fuzzy. Now, if I asked everyone on this call to give me your height, I think you'd tell me. I don't know why you wouldn't, but we don't really politely ask each other our width, do we? That's just not done. But we are kind of cylinders, although it's kind of fuzzy. So let's do some middle school arithmetic here. The volume of this thing is pi r squared times the height. Remember, I can't get a radius. It's some kind of effective radius. Irrespective of our height, we have kind of this fuzzy random variable, don't we? So here's a distribution that's meant to represent the statistical distribution, probably a density function of some kind of radius of our body. And the weight here would be that volume times some effective density. I mean, some of us have hard muscular bodies and some of us are kind of pleasingly squishy. That's what makes the world go around. So my weight here, I've introduced yet another function of a random variable. Maybe it looks like that, I don't know. And these may be correlated. You know, they may not be. I don't know. We have to undertake some scientific investigation to figure that out. So if I collect terms, I've got that my weight here, remember I'm pursuing some notion of height and weight here based on the geometry of my subject here. So I've got this expansion of terms. And remember, I'm not going to get your radius. I mean, I could do some kind of double-blind study and maybe you'd tell me. But I mean, you know, you're not, I'm just, so I have to give up this pipe dream of getting this radius. But it looks like if I take my waist, it's some kind of fuzzy function of my height. Now, this fellow is taller and has the same waist as that guy, so it's fuzzy, so I'm going to introduce yet another random variable. Here it is. I've got another...
Max, I'm so sorry, but I think you have some issues with microphones. Sometimes we're hearing some noises.
Okay.
Sorry for interrupting. Would you try without your headset?
Okay.
Maybe that's better.
How's that?
Yeah, I think that's better. Yeah.
Okay. Thank you, Dahlia. Okay, thank you. So, we gave up our radius here. We've got another power of height times this fuzzy k, which has again some kind of probability density function to it. But if I collect terms here, can you see that I have the weight over the square of height? So I can measure this in the laboratory. And this is Mother Nature here with all of this crazy convolution of these random variables, these functions of a random variable here. And so I'm just going to give that thing a name. You know, we'll call it body mass index. We have to call it something. So my laboratory measurements are here, and the fuzziness is over here. So with that hypothesis, I think that the physics driving this data is some kind of third order feature. So if we itemize our third order features, the cube of each, the square of one times the other, the square of one divided by the other, and one divided by the square of the other, then our hypothesis now is that this ratio should be statistically significant. It turns out that when a ratio is like that, then the reciprocal would be also. That's just a factoid for your machine learning knowledge. But so let's give it a try. So let's mark it up. Now I have here they are. There's all the third orders. But remember, I have a hypothesis now. I'm pursuing a scientific hypothesis. So let's mark up our pre-obesity. Remember that was 1864 of them, and let's do our study. Now this p-value helps me because I'm working against the hypothesis. This is fantastic. There it is. It's strongly statistically significant. I'm so excited. It's a horrible classifier. It's just now we're back where we started. We can't beat the default. My true positives are falling off to like 0, and my threshold is just entirely unsatisfying. What's going on? And what's going on is that the data is very dirty. I mean, you can see this encroaching here. And those of you who have maybe gone through a graduate program or worked in an industrial group, you remember, the theory is one thing, but getting the data is a different thing. I mean, as we speak right now, what is it? It's 8:30 here on a Saturday evening at Georgia Tech. I promise you, there's poor graduate students in the lab, and they're not there working out the theory. The theory's done. They're there trying to find good data. The problem is this data is just kind of fuzzy. So even though I have the physics worked out, I can't converge on the right answer. So I have to undertake a research program here. I have to take a study, and I have to try to predict the left-hand side of this data set, throw away the right-hand side, and then undertake another study to slice off the blue guys from the left-hand side, the purple, black, and blue. So and this research program could comprise, say, hundreds of experiments, maybe taking years, perhaps a whole career. That's the way the science works. So let's do it. Let's get our left-hand side, that's pre-obese, normal, and underweight. I still have my hypothesis here. And let's see now, let's do it. I got 520, so here's my left-hand side. 525, 28, 29, 49 minus 100, so it should be 47, 4750. It's 4741. And I undertake my logistic regression. It is not statistically significant. Well, that's a bummer. I mean, I think I have the physics right, and the reason that's not statistically significant is that the data is dirty. The data is just not good. However, this is a perfect predictor. Now, and I'm showing you, by the way, the training data. You deserve to hold that in contempt. That's not the way we do it. We have to report the testing data. It is also perfectly predicted. I'm not a room on this slide. But so I've done it. So congratulations, doctor. You did it. You get to leave school. The next guy has to go after this next experiment. That experiment is we take only the left-hand side. So this is a subset here. We're taking only the left-hand side, pre-obese, normal, and underweight. Here's my hypothesis. I have to rescale everything because I'm throwing away the whole right-hand side. And I'm going to try to predict only on the right-hand side of the left-hand side. That would be the blue guy. That's 1,860 of them. Let's do it. It's not statistically significant. That's too bad. My data is dirty. I feel like my hypothesis is analytically correct, but it's a perfect predictor. And again, it's also perfectly predicted for the training set I promised. I just didn't show it here. What's going on? Well, and there I did it. And by the way, I'm using here as a metaphor, kind of two slices. This thing could be, that's the solar spectrum, by the way. This thing could be buried somewhere. This transition we're looking for could be buried with miles and miles of experiments to do. There's no promise we can get at this with 1 or 2 machine learning experiments and a little theory. This thing could be in the middle of, it looks like something at 6,000 Kelvin. I don't know what that is. But, metaphorically speaking, we can work very hard for a very, very long time to isolate these effects. So don't misunderstand me that these things can be chopped away at with a couple of experiments. It could be very hard. That was science. I had a hypothesis, and I pursued the hypothesis, and I need some better data. Now remember, there may not be better data. So what am I going to do? I have to go find it. I have to build an experiment and very, very carefully isolate the effect and measure some data. let's change our way of thinking for a minute. Let's take some higher order powers of our laboratory data. Remember, I was only given height and weight, but I'm going to expand it in the square of height, height times height, weight times weight, height times weight. Those are my second order terms. I've got my third order terms, weight times weight times weight. That's weight cubed. Here's my hypothesis, weight divided by height divided by height. That's weight over the square of height. So I've got 15-dimensional space here. So it's starting to look kind of like some kind of an expansion of some function. What function, I don't know. That's what machine learning gives to me. But I'm going to take my laboratory data and I'm just going to go to town and engineer some features. This is termed feature engineering. And let's do our study. Wow, they're all significant. Now, remember, I don't have a hypothesis. Remember, my physics is here. I'm confident of it. So don't, I'd rather have statistical significance than not. But remember, I showed you a good physics hypothesis that was not statistically significant, but still was a perfect predictor. Here, I don't have a hypothesis. Everything is showing some correlation, if not cause. But how does it turn out? It turns out it's a perfect predictor. What you're seeing is a kind of a funny line. Out of 10,000 training samples, there were, I think, a couple of false positives and 2 or 3 false negatives. Again, the testing data was also perfectly predicted. And what's going on? Well, what's going on is we're not doing science here. Remember, we tried that. And we had some success. We have a perfect predictor with our hypothesis, but we need better data. What this machine learning technique says is, well, I don't really know what the physics are. By the way, correlation is not causation, but you can't have causation without correlation. So it's a strong likelihood, if I had no other physics knowledge about this problem, or couldn't, maybe I can't get at the problem. The chances are that the physics is somewhere in this result. Well, we know it's here, don't we? But even if we didn't know that, it's true that that correlation is not causation, but there isn't causation without the correlation. So if we p-hack this thing, maybe we're in the hunt. Well, indeed, remember this thing. We've lifted that into a higher dimensional space, and even though we don't know causation, we're still able to make a perfect classifier. Well, this is actually news. I don't know if you saw in the news cycle a week ago yesterday, but the American Association for the Advancement of Science, Genevera Allen, currently at Rice, took her PhD with Rob Tibshirani at Stanford in that wonderful statistics department of theirs. She gave a speech. She says, listen, these data, and Tibshirani did his PhD with Bradley Efron, a famous professor. You know Tibshirani, I'll bet, from the lasso technique, if you use that in your machine learning. Efron invented bootstrapping that we all use so successfully in our machine learning studies. And Efron did his doctorate with Miller himself, who established the Stanford statistics department. This whole academic family works in genomics, bioinformatics, pharmacological chemistry, things like that. And what Genevera says is, listen, there's a lot of published research in peer-reviewed journals that is not good science. These data sets, she says, look, are very, and this is understandable somewhat, these data sets are very expensive, especially in astrophysics and geophysics, in maritime ocean studies, in genomics. But this thing we're doing where we take machine learning and apply them to these publicly available, huge, expensive data sets, we aren't really doing science. All we're doing is finding patterns in the data. That's what machine learning does so very well. So we're not honing in on root cause. And in fact, these results cannot be reproduced. That is, if someone else takes another machine learning study on these data sets, they cannot reproduce even the machine learning effects. And when new data sets are developed, however expensive or laborious it may be to get them, when new data sets become available, the published research is invalidated. This is not science. This is just machine learning pattern recognition that we're publishing in peer-reviewed journals. And by her estimation, 85% of the biomedical research is actually wrong. So this has to get fixed. It will get fixed, and there's probably no better academic family to fix it than this one. But I just want to use that as some news you can use. It's in the current news cycle. It actually is an issue. It is kind of exciting. I don't want to, give you the wrong idea. These have been a muse these data sets are amused for some fantastic machine learning results. What is troubling to the physics and geophysics and genomics community is it's passing for peer-reviewed root cause science. That's what has to get fixed. So don't mishear me. The machine learning pattern recognition is still a very powerful thing. So Dahlia, I'll stop there. There's so much more to say, but I think that kind of gives us a good comparing and contrasting between pursuing a root cause effect in science using machine learning techniques and using machine learning in its raw form to lift data into a higher dimensional space and to try to draw a decision boundary and start to understand the physics that itself may lead to other data science studies. So I'll stop there.
Thank you, Max. Thank you. That was very interesting. It actually was like a whole lecture from university. So while people are still like processing this information and probably some will have some questions, let me just put some survey about the webinar, a small poll, because we're always interested about the feedback. So I think, Max, you also see this?
I do.
I think so. So yeah, the poll is in progress. And also, let me see if we have any questions right now.
Dahlia, shall I stop sharing, or is it best that I continue to share?
That's okay. Yeah, I think that's fine, because people will have some questions. You might show something.
Okay. Thank you.
I actually have one question. So if the data set is bad, so that means that feature engineering actually helps to improve the data. Is that what, you know?
Absolutely. Yeah, that's a very powerful takeaway. You know, so science proceeds by isolating an effect and taking data, but you know, all of us know when you arrive at a business, especially a business firm, in applied data science, we don't, you know, we have to meet the data where it lies, where it lays. So we can't manhandle the data. The data is the data. You know, as a consultant, invariably I go into even the biggest business firms, global 10, and the first thing they do is apologize and sort of roll their eyes and say, you know, our data is just, you know, is just kind of messy. Listen, the data is always messy. That's the real world. It's only in a scientific laboratory where you can prepare your experiment and take very clean data. And then you need to do that to get insight into the physical world or a biomedical, pharmacologically active molecule or something. Of course, that is science. But in terms of trying to make a decision or a prediction, say in a scoring model like a multivariate regression or some kind of neural network, you know, the data is the data, and it is our job as industrial and applied mathematicians to work with the data however we find it, and the feature engineering is something that can help us lift that into a higher dimensional space, and however fuzzy it may be in that hyperdimensional space, the promise of doing that is that you can slip that hyperplane right through the middle of that stuff and make a good decision.
Oh, okay, I got it. Thank you so much. We also have a question from Baektian. Besides higher order variables, are there any feature engineering techniques you often use in practice?
Well, I showed ratios, so that's a deep question. It's a good question. It turns out, if you can remember your wave transforms and wavelet transforms, in fact, there's a patent sitting right there you can't see that I'm writing, you know, along with my colleague Justin Hobson. We can use wave transforms to try to get periodicity out of especially telemetry streams. So all of your sinusoidal functions, the Haar basis, which is a binomial square basis, is very powerful. Dubochet wavelets are very powerful. So yeah, wave transforms, periodic transforms of telemetry streams especially are very powerful. Everything is a wave. Even the most choppy periodic remedy ticket occurrence database or call center database is a wave. I mean to say, well, I could ask the audience, you know, what is the expectation of the arrival of calls in a call center. Of course, it's Poisson distributed. The parameters of that, remember the mean and variance is lambda, 1 over lambda if you scale it that way, is itself a feature. So all of the wave transforms from your engineering and differential equation studies are features. All of the derivatives are features. I suppose you could integrate something over time or space and consider that a feature, such as, for example, in fraud payment data, all of us have a mean time to spend and a mean time to put money on our card, perhaps our paycheck or something like that. That is a fingerprint, just like any other feature. Zuckerberg has said for years that if he knows on average the first 3 of your stops in the morning, coffee at Dunkin' Donuts, the dry cleaners once a week, and your train station, that he knows who you are. That's quite a statement, but our behavior is a fingerprint, and so all of those geo-coordinates and functions on the geo-coordinates, all of the waiting time densities between our actions, say between getting coffee and boarding a train, are themselves features, and functions on those values are also features. I hope that was responsive.
Yeah, I hope so. Thank you so much. Yeah, the excellent says thank you. Another question from Ram, does meta-analysis of multiple data sets improve the causal analysis?
Absolutely, yeah. That's an excellent question. So one thing we do, especially in academic science, is do our best to understand the same effect across different experiments. If you remember the way that Planck found Planck's constant with his experiment, and all of a sudden Einstein, that was with the radial, the black body energy density. And then all of a sudden, Einstein explained something completely different. He explained the photoelectric effect. And this very same number, Planck's constant, came from 2 very different physics. It was deeply fundamental. Well, I don't do anything that exciting for a living, but the one thing we can do, say, in a business firm is if we have some kind of call center data, we might look for some kind of ordering data or remedy ticket data for outages. Or we can look at the network platform health, say, in a cable television network operating center, and tie that to the call center, so that we can use the network operations center as a probe for what we might find in the call center. If we can predict, I'm fixating on call centers, but call centers are very expensive, and sometimes the return on investment, the measurable ROI for a data science study, is found in something like a call center or a shipping dock or a receiving dock or a rail line, something like that. Was I responsive there, do you think?
Yeah, I think so. Hope from this actually answered your question. Another question is from Becca. Would it be sensible to use SMOTE, S-M-O-T-E, unsampling as a hypothesis in the scenario and applying it to an applied setting? Yeah,
this is a good question. So remember, anything can be a feature, including the results of other studies. Clustering, for example, is a perfect kind of elementary example of that, where the result of the k-means or hierarchical clustering is itself a feature. So I might ask the attendee for an example, for again, the result of I'm trying to think of an example recently. I keep going back to the Network Operations Center, where you have various physics going on throughout the business enterprise, each of which, the results of each of those studies is itself a feature in another study.
So Zach, I hope this answered your question. Another question from Ram: is this better than brute force ML for pattern recognition on the noisy data? Sorry.
Yeah. So quashing noise. So 3 or 4 questions ago, we talked about wave transforms and so forth. removing noise from data is a different topic. So that's an excellent question. It's an important question. And the search for quieting the noise out of data is a different kind of a workflow. In the case of periodic type sensor telemetry, for example, streaming data, that can be done again with wave transforms. The higher frequency, well, it depends on which signal you're interested in, but if you want a low pass filter, for example, you can put in a wave transform to eliminate high frequency signals, to focus, to cleanse or to filter the data set so that you can use machine learning to get at the correlations or cause and effect you're interested in. So yeah, it's an insightful question, and the answer is yes, absolutely. Take whatever liberties you need to quiet the noise out of the data before you do your study. There's no onus on us as data scientists to try to model around the noise. Our goal as business analysts and applied mathematicians is to get the noise out of our data. So when I did make the statement a few minutes ago, we have to take the data where we find it. But I always urge machine learning engineers, listen, data science is first and foremost a science. So all of the math that I hope you got in your engineering program or your physics or physical chemistry or mathematics program is brought to bear on the data. Look for correlations and get them out of there. Look for autocorrelations and heteroscedasticity and get it out of there. If there's high frequency or low frequency noise in your data from some other effect, take full liberty and get it out of your data set before you predict. Yeah.
Thank you so much, Max. Ram, I hope this answers your question. So far, I think no one has any questions. Yeah, I guess that's pretty much it.
Okay.
So yeah, thank you, Max, so much. We really appreciate your time. Today's lecture was extraordinarily interesting, and especially for me, I mean, it was like back into my graduate program lecture. It was very helpful. Yeah, so thank you so much. It was very technical and also helpful. So thank you again. I know you might be tired. You're always traveling. Yeah, great job. Thank you so much. Yeah, we're all looking forward for cooperation with you.
Well, I sure enjoyed my time. I'm grateful for the excellent questions and the chance to see you again and to be involved with ideas. So thanks all around.
Yeah, thank you so much. And everyone for joining us today, thank you so much. And those who are watching YouTube video, next time I hope you can join us online. And looking forward to the next webinar. So thank you again.
Thank you.
All right, this is the end. Bye.